11.3 Definite integrals and net change. Let's look at a simple example. Johan has $50 right now. Every day he saves $10. How much will he have after 4 days? Well, that's $50. He saves $10 for 4 days. 50 plus 40 is $90. The initial value is 50. The net change is 40. So the final value is initial value plus the net change. Now, sometimes we need calculus to figure out the net change. We're going to use definite integrals to do that. That's why this lesson is called definite integrals and net change. For example, Miriam has $30 right now. She saves money that is given by the function f of t. How much will she have after 4 days? Well, she starts at $30. How much will she have after 4 days? Well, we're going from saving from 0 to 4, so we're integrating from 0 to 4. We're integrating our change function, which is f of t. So that's our answer. It's going to be 30 plus the integral from 0 to 4 of f of t dt. Okay. Let's look at an example from position, velocity, and acceleration. The initial position of a particle is 3. V of t is 4t minus 3. We want to find the position at t equals 5. Okay. Well, the net change is going to be our integral of vt dt. We're going from 0 to 5. So it's going to be integral from 0 to 5 of 4t minus 3 dt. Okay. That's equal to 2t squared minus 3t. Evaluated at 5 minus evaluated at 0. When t equals 0, the whole function is 0. So we just have to plug in the 5 part. So it's 2 times 5 squared minus 3 times 5, which is 50, minus 15, which is equal to 35. So net change is 35. So the final position, big F of the final position, x of 5 must be equal to the initial position, x of 0, plus our net change, which is going to be initial position is 3, our net change is 35, so our final position is 38. Okay. Example 3. The rate at which people are entering a store is given by the function f of t is equal to 2 times t minus 3 squared times t minus 7 to the 4th power for 3 is less than t is less than 7. There are 50 people in the store at t equals 3. Part A, how many people enter the store from t equals 3 to t equals 7? So the accumulated change is the integral from 3 to 7 of f of t dt. So it's the integral from 3 to 7 of 2 times t minus 3 squared times t minus 7 to the 4th. On the AP Calculus test, you can use a graphing calculator for this. In this class, you can use Wolfram Alpha to calculate the integral for us. We are looking for we're trying to integrate from 3 to 7 of 2 times t minus 3 cubed times t minus 7 to the 7th power to the 4th power. So we'll let them do the integration. It does the calculation for us, and we get about 468. So that's equal 468. Okay. How many people are in the store at t equals 7? Well, the number of people in the store, let's use big F of t equals number of people in the store at t. Then big F of 7 must be big F of 0, big F of 3, plus our net change. So it's going to be big F of 3 is 50. We start with 50 people at t equals 3. We know from t equals 3 to t equals 7, we got 468 more. So the answer is 518 people. Okay. The reason why we're adding F of 3 plus net change, because the net change here is from t equals 3 to t equals 7. Yeah. And we know this works because the net change in this problem, our definite integral from 3 to 7 of f of t, well, from the fundamental theorem of calculus, we know that's big F 7 minus big F of 3. If we plug that in, we see that that's why it's true. Okay. Next, example 4. Here's a question from the MCAS, graphs. We're given the graph of our rate of change, f prime, our derivative. Let f be a function defined on the closed interval -5 to 5 with f of 1 equals 3. The graph of f prime, the derivative of f, consists of two semicircles and two line segments as shown above. A, for the interval, find all values x at which f has a relative maximum. Justify your answer. What would f look like? We were given f prime. What should f look like? Well, let's draw some axes. Well, from -5 to -3, f prime is positive, so it's increasing. From -3 to 1, f prime is negative, so it's decreasing. f1 is equal to 3, so we know 1 point here. So we know that from -3 to 1, we know it's decreasing somehow. From -5 to -3, it's increasing somehow. Okay. Now, technically, because it's a semicircle like this, we know that it's more like this. But the point is it's decreasing. And from -3 to -5, we know that it is increasing. Actually, so we know that it's decreasing fastest at in between. So we know it looks more like this. And then from -3 to -5, it's also like this. Okay. And then from 1 to 2, it's positive, so it's increasing again. From 2 to 5, still positive until it gets to 4. At 4, it starts decreasing. So we know f of t should look something like that. Okay, part A. We want to find where f has relative maximum. Well, from -5 to -3, it's increasing. We know that f prime is positive from in -5 to -3, negative in -3 to 1, positive in 1 to 4, and negative in 4 to 5, right? So from the first derivative test, so let's give us more space. So by the first derivative test, we know that f has a maximum at t equals -3 and t equals 4. Okay. Because it's increasing to the left and decreasing to the right. Part B, find all values of x at which the graph of f has a point of inflection. So point of inflection means that f double prime, the second derivative is 0. which means that f prime has a slope of 0. And from the graph, we see that f prime has a slope of 0 at x equals -4, -1. Yeah. Now, at 2, there's actually no slope because we make a sharp turn. But slope also changes. We know that f prime also changes from increasing to decreasing at x equals 2. So we have, so f has points of inflection at x equals -4, -1, and 2. Okay. Let's give it our more space. C. Find all the intervals on which the graph of f is concave up and also has positive slope. So concave up means that the second derivative is positive, which means f prime is increasing. Positive slope means f prime is increasing. So we want where our f prime is positive and increasing. F prime is positive and increasing, so it has so f has positive slope and is concave up. We look at our graph again. So there are two regions. The f prime is positive and increasing from -5 to -4, and from x equals 1 to x equals 2. For the intervals -5 to -4, and 1 to 2. Okay. This is a review of what we've learned before. But now part D. Find the absolute minimum value of f of x over the closed interval -5 to 5. We want the minimum. We know that the net change is the area under the curve. And we know that from -5 to -3, this area is positive. So this is positive change. And we know this area is negative change. And then this area is positive change again. Yep. Okay. So by candidate's test, so we know that since f is increasing from -5 to -3 and 1 to 5, and decreasing from -3 to -1, the absolute minimum must be at x equals -5, our endpoint, or at x equals 1, because it has increased and it has decreased. And because it also decreases from 4 to 5. And it decreases from 4 to 5. Or at x equals 5. Those are the only possibilities. Okay. Well, let's think about this. How much has it changed? From, let's give ourselves more space again. From x equals -5 to x equals -3, the net change for f is the area, which is a semicircle with radius 1. So it's pi over 2. Because the area is pi r squared, the area of the whole circle is 1. It's a semicircle, so it's pi over 2. It's positive pi over 2. From -3 to 1, the net change is the area, which is net change is going to be negative, and the area of radius, circle of radius 2, That's pi r squared is 4 pi divided by 2 because it's a semicircle, so it's negative 2 pi. Okay. From x equals 1 to x equals 4, the net change is the area of a triangle with base 3 from 1 to 4 and height 2. So 3 times 2 divided by 2 is 3. It's plus 3. From x equals 4 to x equals 5, the net change is negative this time. Negative of a triangle, area 1/2, so negative 1/2. Right? Okay. So what's happening then? That means that from x equals negative 5 to x equals 1, the net change is pi over 2 minus 2 pi, which is negative 1.5 pi. Right? That means that, so f is smaller at x equals 1 than at x equals negative 5. And this makes a lot of sense because the negative change, this area, is clearly bigger than the positive change, the area there. Okay. Let's give that a little bit more space. And from 1 to 5, the net change is 3 minus 0.5, which is 2.5. So f is larger at our final endpoint, x equals 5, than at x equals 1. So the absolute value, absolute minimum of f is found at x equals 1. And that makes sense. It's going up by a little bit from negative 5 to negative 3, goes down a lot to 1, goes up quite a bit from 1 to 4, and that goes down a little bit from 4 to 5. So the smallest, the absolute minimum must be at x equals 1. Okay. Example 5. The rate at which the amount of money in a bank account is changing is given by f of t, which is equal to 2 times e to the t for between 0 and 4, and 500 minus 100t from 4 to 6. Okay. Is f of t continuous at t equals 4? Well, 2 times e to the 4th power is not equal to 500 minus 100 times 4. I plug in 4 for the both t's. So f of t is not continuous at t equals 4. In fact, if we graph this, we'll see that it's not actually continuous. There's a slight jump. Okay. If we have $300 in the bank at t equals 0, how much money is in the bank at t equals 6? That's really just the integral. We're finding the net change. From 0 to 4, our function is 2e to the t. And then from 4 to 6, our function is 500 minus 100t. Both of them are dt's. When we calculate the integral, we have 2e to the t evaluated at 4 minus evaluated at 0 plus 500t minus 50t squared evaluated at 6 minus evaluated at 4. That's equal to 20 to the 4th power minus 20 to the 0 power plus the second part, which is 500 times 6 minus 50 times 6 squared minus 500 times 4 minus 50 times 4 squared. Sorry about the handwriting. In the notes, you'll see this typed out, so it'll be a lot more neat. We can just use Google to evaluate this. So this is 20 to the 4th power minus 1 because it's 20 to the 0 power plus 500 times 6 minus 50 times 36, because 6 squared, minus 500 times 4 minus 50 times 4 squared. So I get 159,999. Let's change this very quickly. The negative 1 comes from the 20 to the 0th power. Okay. Now that's not the final answer. That's just the net change. We also have the final amount is going to be our initial amount plus our change, which is 160. There should be a 9 just to be more clear. So this is going to be 160,000 and 300 minus 1, so 299. So 160, 299 is the final amount. During which interval is f of t positive and negative? Well, 2e to the t power is always positive. 500 minus 100t is positive for when t is less than 5, and negative for t is greater than 5. So that means that f of t is positive for the interval 0 to 5 and negative for the interval 5 to 6. And that makes sense. When we look at the graph, yeah, it's going up. Well, the derivative is positive from 0 to 5 and then negative from 5 to 6. At what t is the amount of the money in the bank at a maximum? It should be t equals 5, because the total amount is increasing from t equals 0 to t equals 5 and decreasing from t equals 5 to t equals 6. Okay? This is really just the first derivative test. Okay. Summary, what did we learn? We know that the accumulation function is the integral of the rate of change from before. So for example, if f of t, small f of t, is the rate of change of big F of t, so big F of t prime is equal to small f of t, then the final amount, then big F of t, the final amount, is equal to big F of 0, the initial, plus the integral from 0 to t of the rate of change. So it's the initial plus the accumulated change. We don't have to start from 0, as we saw from example 3 earlier. We could start from any other number. So really, more generally, we could just say that f of t is f of any number. Let's say f of a plus the integral from a to t of f of t at. You could also do it that way. Sometimes this integral, we know this integral from a of t of ft, that's just the area under the graph. So we can use geometry to calculate it. We can use Riemann sums to estimate them, and so forth. Okay, that's it for this lesson.